Okay, so hi, welcome to this next video in linear programming. This video is regarding the technical detail that was omitted from phase 2 of the simplex algorithm. We've already made a video discussing the technical detail omitted from phase 1, and this is the analogous video for phase 2. So in phase 2 of the simplex algorithm, we said that the simplex algorithm, when run with this convention called Bland's rule, was guaranteed to terminate. And we just took that for granted in that video, and so in this video we'll prove that, that fact that we took for granted there. So remember, Bland's rule is the convention that says that whenever you have multiple indices that satisfy whatever criteria you're trying to currently satisfy, you always pick the smallest satisfactory index. So if you have a choice, you always pick the smallest one by convention. And then so our goal with this video is then going to be to show that the simplex algorithm, when you use this Bland's rule convention, is guaranteed to terminate in a finite number of iterations. Or in other words, there's no infinite loops that you could get stuck in. Because remember, the idea that we said could happen, that could make the simplex algorithm go wrong in the previous video on phase 2, was that it's possible that you're at some basis in your simplex algorithm, and you run an iteration and you get another basis, and you run another iteration and you're at another basis, and you keep doing some iterations for a while, and then at some point actually you do another iteration at some point and you get back to the first one that you were at, and you cycle bases like that. And if you did, then because there's only one basic feasible solution for each basis. So not only are you at the same basis, it's the same basic feasible solution as well for that iteration. And so then simplex is just going to do exactly the same thing that it did the first time it was at that basis. But the thing it did the first time is what got you in a loop in the first place. You're just going to keep circling around in a loop over and over again forever, and you'll never terminate. But we're saying that when you use Bland's rule with the simplex algorithm, this cannot happen. There's no, you can't cycle through multiple bases. So that's why we're calling this a Bland's anti-cycling rule. There's no cycles of bases. Okay, and so that being true, we'll justify this picture. Once we've proven this fact, we'll have justified the picture we have here, specifically the bottom half, this blue circled part, because if you start with a basic feasible solution and you must terminate the algorithm, well, there's only two cases that you could terminate into. Either you terminated and found that you had an optimal solution, or you terminated and found that your linear program was unbounded. But we didn't. There were no other options for the algorithm to terminate. And once we've shown that the algorithm must terminate, then these are the only two options available. And then you combine that with the fact that we've now completed phase 1. So we've shown not only that in phase 1 what we showed was that either you have an infeasible linear program or you have a feasible solution. And then in the technical follow-up video, we showed that you can construct from a feasible solution, you're guaranteed to have a basic feasible solution for some basis. And so BFS exists for sure. And so this top half was already justified. And so now we're justifying this bottom half in this video. And so this whole picture will be justified. And that will show that the fundamental theorem of linear programming is true, which, remember, that says that there's only three possibilities for your linear program. Either it's infeasible, unbounded, or there's an optimal solution. And there's no other things that can happen for a linear program, and we're proving that by the correctness of the simplex algorithm, phase 1 and phase 2 combined. So we're going to do this part in this video. Okay, so what's the plan? We're going to show that if we run the simplex algorithm with Bland's rule convention, it is impossible to cycle bases. That's what we're going to show. So it'd be like this. You're at some basis B1, and then you run an iteration of simplex with Bland's rule, always with Bland's rule now. It's just part of the algorithm. You get to some basis B2, and then you run another iteration, and another, and you get to basis BQ, and then you run another iteration, and then you're back at basis B1 where you started. And so that would be a cycle of bases. And we're saying it is impossible to cycle bases like this when you run simplex algorithm with Bland's rule. So why does that imply that the algorithm has to terminate then? Well, we're saying here, if you can't cycle bases, then each basis can be visited at most once. Because if you visit it twice, that you've looped around. So there's no cycles. So every basis can be visited at most once in the simplex algorithm. And we have an upper bound for the number of bases. In order to specify a basis, there's n total columns, and I need to make m choices of indices. So there's to give me a basis. So at most, there's n choose m bases. There's some formula for it, but it doesn't really matter what the formula is. It's just finite is the point. So there's a finite number of potential bases. I have an upper bound here, and I can only visit each basis at most once in the simplex algorithm. By visiting a basis, I mean that the current basis that you're at in the iteration of the simplex algorithm is that particular basis. That's what I mean by visiting. So you're going to visit each basis at most once. Then there's at most this many. Then there's at most this many iterations. So then you have to terminate if you can't have more iterations than this. So that's why showing that. So then you'd be done, and so that's why showing that that there's no cycle like this implies that the algorithm has to terminate. So that's what we're going to show. We're going to show that there's no cycle of bases. So the overall claim is this. So simplex algorithm plus Bland's rule implies that there cannot exist a cycle of bases like this. And the proof method will be by contradiction. You're going to assume that you run this with Bland's rule, and there is a cycle of bases, and you're going to derive a contradiction. That's what's going to happen. And so just as a heads up, this video is going to be technical, again, in the sense that it's not so much that any of the individual results are difficult, as long as you're comfortable with how the simplex algorithm works, but it's more so that there's just a lot of results that we need, and it's not really clear where we're going to be going for a while. A lot of things just kind of seem arbitrary when we're saying them, but we need to say all the things that we do say, and then at the end we'll kind of throw it all together, and we will get a contradiction. So that will show that actually no such cycle can exist. So that's just kind of a fair warning in advance. Just be prepared for this to feel a bit arbitrary in terms of what we're proving at first, but I'll try to address where we're going along the way. Okay, so big picture in terms of what things we're going to need to be considering in this proof is we're going to have a partition of the indices, which will be convenient for us to be considering, and it'll be like this. So the only bases I'll care about in this video will be the bases in the cycle that we're assuming exists. So these bases right here in this cycle B1 to BQ. Those are the bases that have been circled. I've drawn black circles here for each of those bases, and then they live within the overall set of all n indices. So brackets n is the same thing as the set 1 to n. Anyways, okay, so the partition is into the red part, the blue part, and the green part, as I've illustrated. So there could be a lot more bases than what I've drawn here. I've just drawn 3 because that's the only way to make a clean Venn diagram. But the picture is still representative regardless. And so the red part will be the indices j minus. So j minus, the red indices, are the indices that never appear in any of the bases in this cycle. So that's the red. Then there's the green overall intersection, which is j plus, and that's the indices that are in all of the bases in the cycle. So so as I'm iterating through the simplex algorithm and it's going through this cycle, we're going to be exchanging indices in and out of the basis. At every iteration you do some exchange, and so some indices will be there at some points and some indices won't. But for the indices in J+, this green set, they are always in the basis at every iteration. It might be the empty set, but it also might not be. So anyways, we're just defining it as it is. So that's the green set. And then finally, the most important of these parts is J0. So J0 is kind of in between minus and plus, so it's kind of neutral or something. And anyways, it's the indices that I've written here. So it's indices J in that are in some basis bi1, but are not in some basis bi2 for indices I1 and I2 in this cycle of indices 1 to Q. Cycle of bases, B1 to BQ, of course. But anyway, so what is J naught? In a more understandable sense, it's the indices that are in the basis of the current iteration of the simplex algorithm at some stages, but are not in the basis at other stages. And so for that reason, we're going to be calling these fickle indices, because sometimes they'll be there and sometimes they won't be. And that's in contrast to the red indices, which are never in the basis, and the green indices, which are always in the basis. So the blues are sometimes there and sometimes not. So very commonly, this J0 set I'll be referring to as the fickle indices. Fickle because, well, that's what fickle means. It's unreliable. Sometimes they're there, sometimes they're not. And then we'll be taking L to be the maximum of those fickle indices, because L at some point, if it's being a fickle index, means it has to exit the basis at some point, and then simplex algorithm is going to have to choose what exited the basis, and so the fact that it had to choose the very largest of these indices, well, and then at some point it's going to re-enter again, and that's going to give us a contradiction. You'll see how that works. So it makes sense to pick the largest of these, because simplex algorithm with Bland's rule wants to pick the smallest index it can. But here, this is the largest, and so the fact that it's going to exit and then at some point re-enter, because we're in a cycle, something's going to go wrong. So it's good to be considering the maximum index. Okay, and so the maximum of the fickle indices is L. So it's a fickle index, so that must mean that it's in some basis B. There is a basis B in this cycle of bases that we're considering, such that L exits the basis, because it's fickle, so it has to leave at some point. And so let's say K enters the basis. So K is entering and L is exiting. So we go from basis B to this next basis, where K enters and L exits. So that's what basis B will be. It'll be a basis such that L is leaving. That's what B will be. Okay, and by the way, just note that K is we're saying K is entering here. So the fact that it wasn't there before, but now it is in the basis, must mean that it's fickle as well. And but since L is the maximum, K must be less than L by the choice of L, because L is the maximum of the fickle indices. So that's just to make sure you're remembering what L is. Okay, and now we're going to do another partition of the indices, and it's going to be like this. So we've already partitioned once, but we're going to do another partition that will be more convenient later on. So you split up the indices into the basic parts and the non-basic parts, whereby the basis B, I'm talking about this basis B, which is the one where it's in the cycle, and then right afterwards L is exiting, so that basis B, and then there's the non-basic elements N, so you split it up into B and N, and then split those up even further so that N goes into the index K, and then just the rest. And then B goes, it's index L. Of course, K is in N and L is in B. That's by what's happening here. And so L is in B, and then the rest you split up as the fickle indices of B that are not in L, and then the non-fickle indices in B. And so that accounts for everything. It's either the basic indices are fickle or they're not. And except for L, we haven't accounted for that. And so here's L. So now it's all the basic indices. And then obviously this accounts for all of N. So that's a genuine partition then. And so then these 5 parts will be the 5 partition parts that we'll be really concerned with. And you can see that this partition set is in terms of the previous partition, because we have J0 here, and J0 was defined in this other partition. It was the blue set. Okay, and so those will be the things that we need to consider. We need to consider that original partition, this new partition that's in terms of it, according to this basis B that we're considering, where the index L, which is the maximum of those fickle indices, is exiting. the basis. Okay, and so here's the setting for the full proof. So it's the usual thing, max C transpose X, matrix non-negativity constraints, and an A is M by N as usual, and it's full row rank as always. And just keep them, just by the way, I should say, right now we're saying this is in canonical form for the basis B specifically, where B is this particular basis that we're talking about above. So assume that we've gotten ourselves to this point where we're going to be at this cycle. Whenever in the proof, whenever I'm talking about the vector C or the vector little b or the vector or the matrix A, I'm talking that data, the coefficients or the vector on the right hand side or the matrix, the data there can change because you have to change it when you go into canonical form for a different basis. At every basis, you need to go into canonical form and update things. And so, the A changes, the little b changes, the C changes. But when I am writing C and A and little b, I mean those are the pieces of data with respect to being in canonical form for this basis B, the one where right afterwards the index L is getting kicked out. So just keep that in mind. Okay, so that's what we do. So here we are, and we're running simplex algorithm phase 2 with Bland's rule, and we're claiming that we can't cycle through this sequence of bases like this. And so here's the proof. So we've already outlined things already, but this is just kind of now formal. So suppose for contradiction that we do enter a cycle like this, B1, B2, BQ, and then back to B1. And what you do, we said already, you partition n into this set J minus, J plus, and J0. So J minus, those are the indices that are never in a basis. The only bases I'm concerned with are the ones in this cycle here. So when I say never in a basis, I mean they're never in any of these bases in this cycle. So J minus is never in a basis. J plus is always the indices that are always in the basis, the current basis. And J0, those are the fickle indices. So sometimes they're in the basis and sometimes they're not. So as we outlined already. And then so L will be the maximum of those fickle indices, and then B is a basis where L exits and some other index K enters. And so we update and go from, at this iteration of simplex, the basis will go from B to B union K minus L. And by the way, I should just mention that, the way I've written it, it's like B1, B2, BQ, back to B1. And so when I say let B be a basis where L exits, L might exit multiple times, right? It could enter and exit the basis multiple times throughout this cycle. So maybe you're thinking, well, okay, so Bland's rule should pick the least index where this occurs. But no, that's because actually this is a cycle. That's the thing. There's actually, even though it looks like this notation, I just needed a notation, but it looks like the way I've notated this, B1 and then B2 up to BQ, it looks like B1 is the first basis and then B2 is the next one and so on, BQ is the qth one. And so, you should pick the quotes first one where this condition occurs, but there is no first actually, because this is actually a cycle. BQ goes right back to B1, and so B1, despite the notation that I've used here for being, just one of the bases, none of them are first. It's just going in a circle here, and so there's no starting point. You could define something arbitrarily, but there's no need. When I say let B be a basis, amongst these, I mean B can be any basis that satisfies this condition. B is any basis where L exits and some K enters. So B is any basis where L exits. I don't care which. This is all fine no matter which basis B you pick. So just pick one and then just stick with it. So we call a particular basis where L exits, that basis is B after that iteration. And so let X bar be the basic feasible solution for B and X prime the BFS for the next basis, B, when you've exchanged K and L. Okay. So how do you go from X bar to X prime? remember, this is a basic feasible solution. So for the non-basic indices, and x bar is with respect to b. So for the non-basic indices, that's n minus k and for k, they're all zeros because that's part of what it means to be a basic feasible solution. The non-basic indices are zeros. And then similarly, for the basic components with respect to b, it's little b. Now going to x prime, what happens? Well, for the n minus k components, they weren't part of the basis before, and for the new basis, where you've exchanged k and l, they're still not, because we're not considering k. It's n minus k here. So x prime there is, they're still all zeros. How about for the k component? Well, remember, k is the component that's getting added on to the basis at this stage. So so that must mean that the associated c coefficient is positive, and x, the associated x component, x prime, we're calling it, is that kth component is our booster variable, and we call the booster variable t. So x prime is t, and we figure out what t is in the algorithm, but I'm just writing t here just to remind you that it means the booster variable. It's the special one that we boost. And okay, so how about for the components indexed by b? Remember, we figured out what those were in the simplex algorithm. It's parameterized by the variable t. So once you know t, then you know what all these basic components, what all these components for x prime are. When I say basic, I mean with respect to b here. Anyways, it's this. We figured this out. It's a little b minus tak, where ak is the kth column vector of the matrix A. Okay, so the reason I just wrote that out is because to get from to x bar to x prime, you imagine these as points in space. And so you have to move in some direction to go from this point in space to this point in space. And so you're moving in some direction, and by direction I mean it's a vector d in Rn, same dimension of space. In other words, I'm writing x prime as x bar plus td. So x bar is some point in space here, and then I add on this vector td, and that takes me to x prime. So I'm moving in the direction of d, and I'm scaling by t. Now, so if I'm writing x prime equals x bar plus td, I've split it up into n minus k, k, and b. So I actually know what d is, this vector d is, in terms of, for these components, n minus k, k, and b. I mean, it's all the components, but if I partition like this, I mean, I know what the components have to be, because, well, you can just see for yourself. I'll come back to it in just a second, but let me just address this point here, which is, that's in general what happens. You scale by t in a direction d, but in our case, though, it's going to be a degenerate case because t must be 0. Because, if t were positive, the amount we're boosting by, if that was positive, then that would boost the objective function value strictly higher than where we're currently at. But then, if that were true, if we were getting a strictly better objective value, then that must mean that there's no way we could come back to the original basis, because for the original basis there's an associated basic feasible solution. You just can't cycle back around, is all I'm trying to say, because if you're getting better and better basic feasible solutions, then the simplex algorithm is never going to make you do worse. You're only going to do equal to where you're already at, or better, in terms of how much the objective function value goes up. Either it just goes up by 0 or it goes up by a positive amount. If it goes up by a positive amount, you're never going to come back to where you were, because it never goes back down. So you can't have cycled back to the associated basis that you were at before. But we're saying we are in a cycle, so that means the objective function value is never going up. That way, that's the only way that we can cycle through bases. And so then if the objective function value is not going up, that corresponds to the fact that the amount we're boosting by is 0. Because we boosted by a positive amount, we'd go up by a positive amount. So t must be 0 for our degenerate case. So actually, x bar and x prime will be the same in our case, but that's just an it's really just almost an aside. We'll have to come back to that point later on. I just wanted to mention it now, but the point I'm making actually here is more general than that. But I did want to mention that when you go for our situation, this basic feasible solution is the same basic feasible solution throughout the entire cycle of these bases. You're never updating it. Okay, so t has to be 0. Anyways, just to address what this vector d is, so d is the direction so this is in general now, I'm talking about in general, whether or not you're at a degenerate case. So in our case we are, but even if you weren't, this point would still hold. I go from x bar to x prime by this direction d, and d has to be, for the n minus k components, it's zeros. For the k component, it's 1. And for the basic components, I fill those in according to the entries of ak negated. I negate the entries of ak and put those at the basic entries of d. Or by basic, I mean with respect to b. And that's what satisfies this equation here. Now, again, in our case, t is 0, so, there's no constraint on what d is. But in general, t doesn't need to be 0, and so I do have a constraint on what d is. But in either case, this d does satisfy what we're at. And in general, this is the only d that satisfies it. So this genuinely is always the direction d. It's given by this. And yeah, let me just say that x bar is 0. So for the n minus k components, for instance, we have 0 plus t times d is 0. So I get 0 plus 0 equals the equals x prime, and that's 0. And so that's true. 0 plus 0 equals 0. Now how about for the k component? I have x bar k is 0. I have 0 plus t times 1 is t. So that works. That's consistent too. So choosing d to be 1 made this equation consistent. And how about for the basic components? I have x bar for the basic components is b plus t times the basic components is minus ak. So I have x bar is b plus t times minus ak, or in other words, b minus tak. And look, that is what the left-hand side is. It's b minus tak. So these choices of the components for d are correct. Okay, and so d, like I've said, d is a direction. You're going from x bar to x prime. And if you saw the previous video, you don't need to see the technical video on phase 1 to understand this video. But if you did, d is what we call a good direction there. It turns out that it is. It's not clear right out of the gate that it is here, but it is. And so if you know what a good direction is, this fact won't surprise you, which is that d is in the null space of the matrix A. So that's the first fact that we're going to use here. So in other words, A times d is 0. So we can figure this fact out independently or not. That's part of what it means to be a good direction, but we can just show it independently here. So what is A times d? You can just compute it very simply by breaking it up into the corresponding components here. N minus k, k, and b components. So for the n minus k components, the d is 0. For the k component, d is 1. And for the basic b components, d is minus ak, and the a is the identity matrix, because we're in a canonical form. A is in canonical form with respect to this basis b. So this is what I get for this next line. And then a times, a n minus k times 0, those are all zeros, so it just becomes 0. Ak times 1 is ak, and then I times minus ak is minus ak. So 0 plus ak minus ak is 0. So a times d is 0, so d is in the null space. Okay, so that's the first fact we need. So here's a relevant note that will become relevant almost immediately. It has nothing to do with this first fact right out of the gate. Like I said, things are going to seem arbitrary for a bit, but I'll tell you where we're going in a few more minutes here. So, but anyways, let's address this note here. So at some iteration, L must re-enter the basis. It has to, because we're in a cycle, and L was in the basis B originally, and then it exited after B. So since it was there originally, it must come back again at some point. Maybe L re-enters the basis once you go through the entire cycle and you're back at B, or maybe it enters earlier. It re-enters earlier. So we don't know. Let's just say that B hat is the basis for which L re-enters the basis. So the first time, we'll say. So it's the first time that L re-enters the basis after it exited after the basis B. So it left at B, now it's coming back at B hat. And so what I mean, let's not be off by one here. Here's what I mean when I say re-enters. So it's not in the basis B hat, it's in the next basis. So at the basis B hat, you then run your simplex iteration, and then the new basis is going to be B hat, and then you've added on L, and then you take out some random thing. I don't know, I just put an asterisk there for whatever exits. We don't know, and we don't care, but that's what I mean. So it enters upon iterating at the basis B hat. So that's when it gets added on. Okay, so yeah, L exits at B, and it re-enters at B hat. Consider the associated objective coefficients C bar for this particular basis B hat. I probably, in retrospect, I should have called this C hat rather than C bar because it's associated to the basis B hat, but it's okay. We won't need this for long. It'll be fine. But anyways, so C bar, these are the coefficients. They're in canonical form for the basis B hat. So remember, C is the coefficients in canonical form for basis B. So they can change to be in canonical form for basis B hat. So that's C bar. Yeah, so that's what this comment is saying here. So, they're different because they're in canonical form for a different basis, but actually we can relate them back to the original basis B. And that's what this fact 2 is saying. So C bar, it's in canonical form for B hat, but I can actually write it as C minus A transpose Y for some Y in Rm, where C and A, those are with respect to the basis B, remember. They're in canonical form for B. So if I transpose everything, it's C bar transpose equals C transpose minus Y transpose A. So C and A are in canonical form for A, and for some linear combination of the rows of A, that's what Y transpose A is, it's a linear combination of the rows of A, then, anyways, C bar can be written in this format. So here it's for B hat, and but on the right-hand side I can realize it in terms of the basis B, as long as I pick the correct vector Y. I don't know what it is, but this is just the format that it's of. So yeah, so the same initial matrix A, regardless of the updates. And by updates, I mean like you update it for canonical form for each new basis that you go to from B all the way down the line to B hat. But yeah, despite that you've updated all these times, you can still keep it in terms of the original matrix A and vector C. Okay, so anyways, what's the proof of this? So we can see that it's true, like, at the first update of this vector C for canonical form, what happens? So, at the first, I mean, like, you start at the basis B, and then you do this iteration, and that puts you in this new basis, B, where you've exchanged K and L, you've added K, taken out L, and now you have to put things in canonical form for this basis here. And so what happens? It's how do you update? You go from C to what happens is it's the same. It's the original, or I should say that it's the prior C here minus Y transpose A, but here we specifically know what Y is. It's exactly this. It's AB inverse transpose times CB. And that comes from the canonical forms video. We showed that was true from the video on putting things in canonical form for a basis. And so all this A and this C, I'm talking about this data in terms of the basis B, canonical form for basis B. But when you but this is what it becomes. This is what the C vector becomes for the new basis. Okay. Anyways, you can see that it's of the right format here. C transpose minus Y transpose A. That's the format that we wanted it. Here we explicitly know what the vector Y is, but I don't need to know in general what Y is. I just need it to be of this format, C transpose minus Y transpose A. Okay, so that was for the first update. How about for the next update? For the next update, so I go from the basis B union K minus L to some other basis, whatever that is. So how do you update the coefficients? Well, it's the original coefficients here. It says, well, I mean, the new original, I guess. So it's whatever they were originally, before, and now it's those. So you update it to be that minus some linear combination of the rows of the new matrix A. Now, when I say the new matrix A, that's quotations A, right? Because I don't really mean the matrix literally A, because literally the matrix A is in canonical form for the basis B. But this new quotes matrix A, that's just a placeholder representing just the matrix. It's whatever the matrix is when it got put in canonical form for this basis, B union K minus L. So it's not A, because A is in canonical form for B. It's whatever the matrix is for this basis. Actually, we know exactly what that is. We have a formula for that based on the video from the canonical forms video, which is this. It's AB inverse times A, where here I do mean, I didn't put quotes here because I do mean exactly the matrix A in both of these cases. So this overall thing is the new matrix quotes A, where that's the matrix that's in canonical form for this. And okay, so that's how you update the new coefficients for the objective function. And also you can figure out what the y tilde here is, but we don't need to. It'll be fine. You just reassociate the multiplication here. Instead of doing this multiplication first, you reassociate the parentheses like I did and do this multiplication first. And that'll give you some other vectors, so y tilde times AB inverse. That's some other vector y double tilde transpose times this matrix A. And then I just factor the A out. So it's C transpose minus Y transpose plus Y double tilde transpose A. And that's just some other vector that I'll call Y triple tilde transpose. So there you go. C transpose minus some vector times A. And I don't know what it is, but it doesn't matter. The point is that it's of the correct format. That's all we'll need, is that it's of that format. And so that was for the next update. And so now, inductively, you can just see that that always happens. Because if it was of the correct format before, and then we update, and it's still of the correct format, then, yeah, you can keep iterating, and it'll always be of the right format. Okay, so you have to iterate enough times to get from the basis B to the basis B hat. But we've just shown that at every stage, you can always, for some vector y, that whatever that vector y is, it might change at every iteration, but no matter what, there is some vector y that makes that work. That makes us able to write C bar as a C bar transpose equals C transpose minus Y transpose A, where the C and the A are with respect to B. Okay, so why were those things relevant? Well, we're going to combine those two previous facts into this. So this will be kind of the key fact that we need, which is that C bar times D, so C bar transpose D, is equal to C transpose D. So even though we're at two different bases, B and B hat, when you take the dot product with D, for C and C bar, you get the same thing, and that's simply because C bar transpose D, well, I am now going to use that fact that we just established, which is that even though C bar is with respect to the basis B hat, I can rewrite it in this format, where this format is with respect to the basis B. So C bar equals this times D, and I just distribute the D in, and then I already showed that A times D is 0. So I have C transpose D times Y transpose times 0. So it doesn't actually matter what the Y transpose is. It's getting times by 0, and so it just goes away. So I just have C transpose D And so there you go, they're equal. So why is that fact relevant? Well, what's going to happen in the remainder of this proof is, so we've just computed this, and we just showed that they're equal. We are going to contradict this fact, actually. That's going to be our contradiction. We're going to do another computation where we split up the components of these vectors into the partition that we had mentioned earlier, the k, n minus k, l, b intersect j non minus l, and b minus jl, j0. When you split it up into those parts, and then you recompute this for those parts individually one at a time, you'll get that these are not equal, and that will be the contradiction. So so what I'm going to do is I'm going to write a table here, and I'm going to fill in what the components, what the signs are actually. But anyway, what the signs of the components of each of these three vectors are for these partition parts of the index set, and then when you do the multiplication again, you'll find that actually C transpose D is not equal to C bar transpose D. So yeah, you could imagine doing that, and if you just wanted to take my word that that's what happens, you could just be done now. But of course we'll keep going. You can see how it works. The main thing to worry about that won't make this super straightforward, well, there's two things. One is that it's not clear right out of the gate what each of the signs of each of these components are, so we have to do some work to figure all those out. And the other issue is that C bar, you have to be aware here, C bar is the objective coefficients for the basis B hat, not B. And yet, on the other hand here, but we've partitioned this index at n in terms of B. This partition here, this is in terms of the basis B, not B hat. So we're going to have to convert C bar from being in terms of B hat to being in terms of B. So that'll be a separate step that we have to do. So what we're going to do is we're going to determine C, D, and C bar component-wise according to these components. And we'll do that. So we're going to start with C bar because that's kind of the one that's different because it's in terms of B hat first. So we'll deal with that first, and then we'll do the others. So we'll do C bar, and then C, and then D. And then we'll multiply again, and we'll find that they are no longer equal in the sense of fact 3 that we just established here. They're no longer equal. Okay, so let's do that. So first we have to convert. We're not going to write the parts of C bar in terms of that partition above right away because we have to convert. So let's do the conversion first. It's not clear at all how this would work, but it's only clear once it's been done that this is how you should do it. But anyways, I'll show you how it's done. First, take a look at the J plus components. So I mean the partition here, we're going to partition C bar in terms of that original partition, the J plus, the J0, and the J minus. And then we'll use that partition and then convert into this other partition that we care about. Okay, so for the J plus components, C bar is 0. We don't have to even think about that. Why is that true? It's because C bar is in canonical. Oh, I should just say, here is I've computed the signs for all the terms, and then on the right here in blue, I've and a little green, I guess, but mostly in blue, I've written the reasons for why all these things are true. So okay, so what's the reason for C bar being 0 for J plus? It's because J plus is part of, by definition, it's part of every basis. So in particular, it's part of this basis B hat that we're currently working with, and we're in canonical form for this basis B hat. So all the components of B hat are 0. So in particular, the J plus components are 0s. Okay, how about L? What's C bar L? That's positive because L is entering the basis at B hat. So we're going from basis B hat to this next basis, B hat union L, subtract something else off. So we've added this index L in. So how could we have chosen to add the index L in? Well, how does Simplex algorithm ever choose how to add a new index into the basis? Well, that corresponding coefficient it had to be positive. So C bar spell had to be positive in order for L to be even a candidate to be entered into to the basis. So simplex algorithm must have selected something positive and then entered that. And so since L was the thing that got entered, it must have been positive. C bar L was positive. Okay, so that was the L component, and L is one of the fickle indices. Now we're going to do the rest of the fickle indices. So that's these next two parts here. So so how about for the fickle indices that are part of the basis, b hat? Well, those are also zeros because, again, we're in canonical form for this basis b hat, and these are just the fickle indices that are part of this basis. So it's a subset of this basis b hat. So yeah, so still zeros because same reason we're in canonical form for that basis. And okay, and how about for the rest of the fickle indices? In other words, the fickle indices that are not part of the basis b hat, and also it's not L. Those are less than or equal to 0. And why is that true? Well, imagine it was otherwise. Imagine that you had some index S in that set of indices where C bar S was positive. Well then, you know, S was less, you know, S is fickle amongst other things. It's not part of the basis b hat. It's also not L, but it is fickle. And we said L is the biggest of all the fickle indices. So S had to be less than L then. And but if C bar S were positive, then you know, that would have contradicted Bland's rule, because by convention of Bland's rule, we should have added index S or something even less. But anyways, something less than L. You know, at least the index S, something maybe even earlier. But no way L was the right choice, because we had coefficients of you know, C bar coefficients that were even less, that were positive, indices that were even less that were positive, and so Bland's rule would have picked one of those if they were positive. So then there's no way it could have been positive. They all had to be less than or equal to 0. So for all those components, C bar is less than or equal to 0. And actually, so the relevant point here is I'm going to combine these two. So the fickle indices that are part of the basis b hat and the fickle indices that are not part of the basis b hat, except for L. And so that accounts for all the fickle indices except for L. And so those are all less than or equal to 0. So 0 or less than or equal to 0. All we really need is that all of those are less than or equal to 0. And then finally, for the remaining part, which is the J minus indices, we just don't know. But it won't matter. We have sufficient information here. Okay, and now we can fill in the table once because we've done this intermediate step, and now we're going to be able to fill in the table. So how do we do C bar for this partition, where this partition is with respect to the basis B? Well, for index K, C bar is less than or equal to 0, because K is, you know, we said that all the fickle indices except for L, that C bar was 0, less than or equal to 0 for all those. And K is amongst those. K is one of the indices that's fickle, but it's not L, and so C bar K must be less than or equal to 0 then. Okay, for the n minus k indices, we just don't know, because part of those will be j minus, and we can't say for j minus, so can't say for these, but, oh, thanks, my device isn't fully protected. I'll make a note of that. All right, the n minus k is unknown, but again, it'll be sufficient. The rest of the information will be sufficient. We don't need that. For the L component, C bar L is positive. We already did that one individually, so that's already just taken care of. And we did that above. Okay, how about for the fickle indices that are basic with respect to the basis B, that are not L? Well, we said that for all the fickle indices except for L, they're all less than or equal to 0. And so, of course, the fickle indices in this particular basis B that are not L is a subset of that. So these are all less than or equal to 0 then. And finally, for the indices in the basis that are not fickle, well, then if it's not part of the fickle indices and it's still part of the basis, then they must be part of the J plus indices. Because if it's not part of J0, that means they never, you know, they're not fickle. They don't come back and back and forth in terms of the basis. They don't enter and exit, and anyway, it's just the partition, right? If you're not part of J0, and you're also not part of J minus, because it is in the basis, so it can't be part of J minus, and it's also not part of J0, then it must be part of J plus. And we computed for J plus how that worked. So B minus J0 is part of J plus. So we already said that for J plus, all those components were zeros, so then all these components here are zeros. Okay, so that one took a bit of work because we had to do that conversion and fill in the table here afterwards. But we've done it. We've filled in the components, the signs of all the components of C bar with respect to this partition. So now we're just going to do it for the other two vectors as well. But they should be a bit simpler because they're already cast in terms of the basis B, both for the vector C and for the vector D, while C bar was not. So these will be easier, especially C. So C is what we do next. So we can just directly ask what the signs of each of the components with respect to this partition is right out of the gate. We don't have to do any conversions. So CK, that's positive. Why? Because remember, C is with respect to the basis B, and in the basis B, we're saying K is what enters directly after basis B, and so the simplex algorithm, again, if we're choosing something to enter the basis, that must mean that the corresponding coefficient in the objective function had to be positive. That's how simplex algorithm works. So CK had to be positive. For the n minus k components, again, we're not going to know, but again, it won't matter at the end. We'll have sufficient information otherwise. For CL, okay, and actually for the rest of these, okay, well, CL is 0, and that's because C is in canonical form for the basis B, and L is part of the basis B. So for all basic indices, where by basic I mean with respect to this basis B, C is going to be 0 by the fact that we're in canonical form for this basis. And so CL is 0, and then all of these are zeros for the same reason, because the rest of these are also part of the basis B. It's either fickle indices that are part of the basis B or non-fickle indices, but still part of the basis B. Either way, all part of the basis B, and we're in canonical form for it. So they're all zeros. Okay, so that one's a lot easier to figure out. We've just filled in the table right here. And now there's only one more to do, and it's D. So the vector D, let me just remind you what it is. For the n minus k components, they're all zeros. For the k component, it's a 1. And for the basic components, with respect to B, it's the vector minus ak. So I look at the matrix A, and I look at the kth column of it, because remember, k is the index that's entering the basis after B. So yes, we know what k is. And I just look at that corresponding column in A, and then I negate it, and I fill in those entries for the basic entries. So I mean, hopefully it was clear, but these entries don't need to come in order that they've been written in here notationally. This is just notation indicating that for these indices and for these indices and for these indices, those are the entries. But these are all probably going to be interleaved together. I'm just kind of separating them out here because we only need to do the multiplication component-wise. Okay. Anyway, so for the k component, again, we're going to break it up according to the same partition. So dk, the k component is 1, which is positive. And I can see that it's 1 because it's already explicitly written here as 1. For the n minus k components, again, they're explicitly written already, and those are zeros. So we've done that part. Now for the rest of the components will be part of the basic components B. So for DL, and for the basic components B, that's all part of this vector here, minus AK. So for DL, that is, it's going to be minus ARK, so for some R from 1 to M, right? So here's the matrix A, here's the column vector AK, and then I negate that when I put it in the vector D here, and so it's a minus, and I'm just going down the entries, and it's just one of those entries, right? Going down the entries here, so I'm going down the entries here, and so for, let's just call it the rth entry down, that's the one that that DL is. Okay, so DL is minus ARK for some R, where as we're going down the entries here, that's corresponding to going down the rows of the matrix. So for some row index 1 to M, DL is equal to minus ARK. And we're saying that that's negative, or equivalently that ARK is positive. So why is that true? Well, L is the rth basic index with respect to B, right? We counted we counted R entries down in the basic indices because this AK as you go down, these are with respect to B here. So once you go R down, that's when you get to this component DL. So L is the rth basic index, and okay, but we know that L is exiting the basis upon this iteration. So what does it mean to be exiting the basis? What do the rules of the simplex algorithm imply then? Well, that must mean that for that component, that ratio, the amount that we boosted by, which is t, had to be realized at this point, br over ark. So for that entry, because L is the rth basic index, corresponding to this entry here. So I had to realize the amount that we boosted by t to be this ratio, which was the minimum of, so this first equality here, this first equality, that's by the rule of the simplex algorithm. That's how simplex algorithm chooses which index exits the basis. So if the rth, if a particular index is exiting the basis, then amongst the base, it's one of the basic indices and current basic indices, and the one that exits, which is so it's the rth one here. The one that exits had to realize had to be equal to this value here, this ratio. That's from the simplex algorithm, and that value, how is that determined? Again, simplex algorithm says it was the minimum of these ratios. It was that's how we defined how much we could boost by, because otherwise we were going to violate the non-negativity of the new basic feasible solution if we push t any larger than this. That's how we came up with this. But anyways, that was from the simplex algorithm. So this realized this minimum of ratios, and in particular, these denominators, the AIKs, were all positive. So in particular, that means that ARK is positive. And so there you go. So ARK is positive, and so minus ARK is negative. So the fact that L is leaving implies this. I should also just mention here that the amount that we're boosting by, in fact, is 0 in this case. Because remember, I mentioned earlier that we are in a degenerate case where the boosting amount is 0, because if we're cycling around, there's no way you can increase your objective function value, because then you could never get back to where you were originally, because that would imply you're at a lower objective function value, and that just will never happen in simplex algorithm. You can only go up. You might stay where you're at, but you're not going down. So anyways, yeah, so the amount that we boosted by here had to be 0. So this will become relevant in just a moment, right now actually, for this next part. So anyway, so we figured out what DL is. Now how about for the next part, which is the fickle indices that are part of the basis, but it's not L. We accounted for L separately. For those, we're saying it's greater than or equal to 0. So why is that? Well, again, we're going to see what happens if a component was negative. So if I have a D component that's negative, remember what D is. It's a bunch of zeros, a 1, and then for the basic indices, it's this. And so in particular for the non-basic indices, n minus k and k, those are 0 and 1. So they're not negative. So the only chance of a D component being negative, that occurs only at these basic indices. So if I have a component dj that's negative, that must mean that j is a basic index. So let's say it's the sth basic index for some row index s from 1 to m. Just how we said above that L is the rth basic index, so j is the sth basic index. Being the sth basic index, then that must mean that dj, it's a basic component, so dj must be minus ask, and we're saying that that's negative. That's what we're assuming here. It's negative. So dj must be minus ask, which is negative. And so equivalently, ask must be positive when I divide by the minus there. And okay, but that's going to be a problem then, because if j is, so now let's suppose not only j is a basic index, but let's suppose it's one of these indices that we're currently considering, the fickle basic indices besides L. Well, if it's fickle, then it must be less than L, because L is the largest of the fickle indices. But if j is less than L, and j is the sth basic element, and L is the rth basic element, index I should say, then well, then that must mean that s is less than r. Because, if you just think about it for a second, if I have the indices 1 to n, and then I've circled in green the basic elements, and I count s down, and I get to the index j. So okay, and then I count r down, and then I get to the index L. So I got further, I got to L when I counted R down than when I counted S down, because I only got the J there. So then that must mean that R must be greater than S, because I'm still counting only amongst the green circled basic indices there. So S must be less than R. But that's the issue. If S is less than R and ASK is positive, that means that the simplex algorithm with Bland's rule would have chosen the index S before R. And that contradicts the fact that we are choosing R, the rth basic index, which is L, to be the one which is exiting the basis. We're saying L is exiting and L is the rth one, but I would have chosen something even earlier if I had the opportunity, which would have occurred if ASK was positive. Remember that it actually doesn't matter what the ratio is. Like usually we're concerned with the minimum of these ratios, BI over AIK, where these AIKs are positive. But in this case, they're zeros. They're all zeros, because the amount we're boosting by is actually 0. So the minimum is 0, and so the only thing that we need to be concerned with is amongst the AIKs. Since these are all going to be zeros, the only thing that matters is which of the AIKs is positive, and then amongst those, Bland's rule will pick the least index, which is positive. So the only thing that matters here, because t equals 0 in this case, this minimum of these ratios is 0, that's the only thing that matters. Usually, we would have to take into account what is the minimum, but we know that we're in this degenerate case of the minimum of those ratios being 0. So the only thing that we need to consider is it's actually arbitrary which one we pick usually, but when we're doing Bland's rule, we need to pick the least index. So we should have picked we should have picked the sth basic index, which corresponds to index j, but we didn't. J is less than L, and we picked L to be the one that exits the basis. That's what's happening here upon this iteration at the basis B. So there's no way that that this could have been negative then for any of these indices that are fickle and basic besides L. So they all have to be, they can't be negative, they must be greater than or equal to 0. So that's why. That's why this component D, for these components of D is greater than or equal to 0. Okay, so that one was a bit tricky, but you'll be glad to know that for the last part, for the B without J0, we don't know what D is for that, and we don't care. So that'll be good. And so yeah, here it is. We've filled in D. Again, D is this, and we've filled it in for all these partition parts for the table. And so now we've filled in the entire table. So now we can finally cash in on that promise that I made at the beginning, where we're going to recompute everything and arrive at a contradiction. So this is it. So we filled in the overall table now, all the signs with all these components, and now let's redo our computation of C transpose D and C bar transpose D. So we said originally that they're equal. C transpose D equals C bar transpose D. So then if I take the difference, C minus C bar transpose D, that should give me 0. The difference is 0 because they're equal. So 0 equals that. And so let me just call this C minus C bar. Let me just call it C tilde, just for more notation. And I'm just so I have one computation to do. Let me break it up into the 5 parts here according to this partition. And let me look at the signs of each of these parts. So it's C tilde times D for each of those parts, and the C tilde is the difference of C and C bar. So let's do parts 1, 2, 3, 4, and 5, corresponding to these 5 partition parts. So for part 1, we have C minus C bar times D. Okay, so it's left minus right times middle. So I have a positive minus something less than or equal to 0 times 1. So positive minus less than or equal to 0, that's positive then, times 1 is positive. So part 1 is positive here. Okay, so for part 2, I have I don't know minus I don't know, so I still don't know, and then I times it by 0. Okay, so that's why we didn't need to know, because we did know for D what it was, and it was 0. So when you times by 0, you just get 0 for the second part. For the third part, we have 0 minus something positive, that's negative, and then you times by D, and that's negative, so then negative times negative is positive. So part 3 is positive. And then for the next part, 0 minus something less than or equal to 0, that's greater than or equal to 0, and times greater than or equal to 0, and you get, again, greater than or equal to 0. And then last part, we have 0 minus 0 is still 0, and then times D, which we don't know, but in this case we do know the C minus C bar is 0, so that shows why we didn't need to know this part. So anyways, when you do the multiplication, it's 0, so part 5 is 0, and now we just add all 5 parts up, because we broke it up into those 5 parts, and you see that we have a positive plus 0 plus positive plus greater than or equal to 0 plus 0, and that then is strictly positive. So it's strictly positive, and that is a contradiction with the fact that it's supposed to be equal to 0, because these two, C transpose D and C bar transpose D, are supposed to be equal, and that is our contradiction. So finally, we got there. So that's it. So therefore, there cannot be a cycle, because if there was, you could go through this entire list of things that we've just gone through this entire video, and you'd get this contradiction. So there cannot be a cycle when using Bland's rule. And so therefore we can conclude that that simplex algorithm, when you use Bland's rule, it visits each basis at most one time. And since there's a finite number of bases, then that must mean that simplex terminates when you're using Bland's rule, because we can only do each visit once, at most once. So there you go. So that shows that simplex algorithm terminates when you use that convention. Whew. All right, that was pretty exhausting for me too. But I told you that was going to be technical. But I just kind of wanted to do that for the sake of completion, so that we had everything covered for the simplex algorithm, which is kind of just such a super important algorithm in really all of math, not even just in optimization, but just all of math. It's one of the most important, kind of a crowning jewel. And so anyway, so we got to be complete for that. And so this is kind of like a end of a stage of linear programming, because all we've done so far is it was all simplex algorithm related. It was first we did we did the preliminary stuff, which allowed us to formulate the simplex algorithm. So it was preliminaries, and then we formulated the simplex algorithm. We gave the algorithm in terms of the 2 phases, and then we showed mostly that the algorithms were correct in those videos, but there were still some things that we had to tidy up, which were these technical videos. So we addressed lingering concerns with these supplementary videos for phase 1 and phase 2, and that's where we're at. So it was lead up, then the algorithm, and then cleanup, and that's where we're at. So everything's been the simplex algorithm so far, but there's more to linear programming than just the simplex algorithm, of course. So I plan to go through more topics, and starting next, I had mentioned earlier that the next thing to do is geometry. That's the next thing to do, and in fact, we can not only are we going to get a geometric perspective, but we can in fact see how simplex algorithm works in this in light of the geometry that we'll discuss. So So we'll get a more intuitive understanding of what simplex algorithm is actually doing. But yeah, so that'll be the next topic. Then there's of course more topics after that, but that'll all be for future videos. But that's it for this video at least. So so if you did, thank you for watching.